All right, welcome back. What we've done so far in this video series is we learned how to connect determinants to solutions to systems of linear equations, first using something called Cramer's rule, and then using determinants and adjoints to create the inverse matrix, A inverse, and going back to the method of inverses and solving systems of linear equations that way. I'm going to show you some strange looking examples where you're not given a matrix, you're just given features of the matrix. You're given little pieces of data, and then based on those tiny fragments of data, what else can you tell me? It's a little bit like a detective novel. So A is a 4x4 matrix. That's the first clue. We're told that the determinant of A is -2, and then we're asked to find the determinant of the adjoint. We cannot get the adjoint of A because we don't have A. So how on earth are we supposed to calculate the determinant of the adjoint? Where is that going to come from? Well, here's the method. Here's the approach. Adjoint of A. We can say actually that we're going to use this fact. We're going to use the fact that A inverse is equal to 1 over the determinant of A times the adjoint of A. What we're going to do is we're going to cross multiply. Multiply both sides by determinant of A. So determinant of A times A inverse is equal to the adjoint of A. Now we can ask the question in a different way. Instead of asking for the determinant of the adjoint of A, we can say then determinant of the adjoint of A is now equal to the determinant of the determinant of A times A inverse. Just replacing adjoint of A with what it is equivalent to. Now you say, you made it worse. Like, it was bad and now you made it more bad. What are you doing? But wait, it's not that bad. We're actually almost done. I'll tell you why. Recall from 4.2. From section 4.2, recall that the determinant of k times A is equal to k to the power of n times the determinant of A if A is n by n, where k is a scalar. What happens is when we multiply a matrix by a constant, every row gets multiplied by that constant. Inside section 4.2, we learned that we can take constants, we can factor a constant out of each row. If we have an n by n matrix, that means we have n rows. So we take that constant out of row 1. We take the constant out of row 2. We take the constant out of each row. There's n of them. So we'll have k times k times k n times, which is k to the power of n. Now the determinant of A is just a number. It's like a k. So the determinant of the determinant of A times A would just be, so this is a scalar, determinant of A is a scalar, it's a number like k. We're going to take that out front. We're multiplying that matrix by that scalar each row. We're going to factor that scalar out of each row. So we have the determinant of A to the power of n multiplied by the determinant of A using that same logic. So we're going to use that here. Based on that result, on that remarkable result, we have that this is equal to We're taking that constant out how many times? It's a 4 by 4 matrix. So we're taking it out 4 times. In the above 4 by 4 example, n is equal to 4. Okay, so determinant of a to the power 4 times the determinant of A inverse. Okay, but it's still yucky. What are we supposed to do? We don't have A. If we don't have A, how do we find A inverse? So we can find its determinant. And the answer is earlier. It's from earlier on. We also know, what is the determinant of A inverse? It's 1 over the determinant of A. We saw that before. So we need that shortcut as well. Determinant of A power 4 times 1 divided by determinant of A. Let's plug in the numbers that we were given. We were given that the determinant of A was -2, so we have -2 to the power 4 divided by -2. So that'll be positive 16 divided by -2. -2 multiplied by itself 4 times. Positive 16, and we get -8 for that answer, and that's it. We shouldn't really say that's it. There's a lot of stuff on the left-hand side, and that's just the justification for our calculation. So some things would change. For example, if A was a different size, if it was 3 by 3, what would change is up here, that we would have this being a power 3 instead. Would anything else change? No. Everything else would be the same. If we change the determinant of A to something else like -5, well then you get a -5 to the 4 and then divide by a -5. It is a fairly straightforward question once you know the idea of what to do. Okay, let's look at a similar weird calculation. A is 3 by 3, determinant of A is equal to 4, find the determinant of the adjoint of A. I'm going to start again that A inverse is equal to 1 over determinant of A times the adjoint of A, and then cross multiply so that adjoint of A is equal to the determinant of A times A inverse. So our determinant of the adjoint of A is now equal to the determinant of the determinant of A times A inverse, with n equals 4, or n equals 3, sorry, n is equal to 3, since 3 by 3. So we're going to factor out that scalar, determinant of A. We're going to factor it out once for each row. So we'll have the determinant of A to the power of 3 times the determinant of A inverse so determinant of A power 3 times 1 divided by the determinant of a, which you can simplify. You can write this as determinant of a to the power of 2. You have 3 powers of something on top, 1 power on the bottom. You use your exponent laws if you want. And I'll explain that. We have x squared, or rather x cubed over x is x to the 3 over x to the power of 1, which is x to the power of 3 minus 1, which is x to the power of 2 using exponent laws. Or I'll just do what we did in the last example. Like we could have used exponent laws here, just determinant of a to the power of 3. Just doing it in 2 different ways. Some people like to use the laws of exponents, some people don't. So you have an option. You can do it this way without thinking about exponent laws, just plug the numbers in and simplify. Or if you like using the laws of exponents, you can do it this way. Okay, so our data says that this is 4. So we have 4 to the power of 2, which is 16. That'll be our answer. Yes, there's shortcuts. Yes, there's weird formulas that you can use if you don't want to understand what you're doing. And you can figure out what those formulas are on your own if you want. But I'd rather explain why this number comes out and not just give you the useless, or not useless, give you the meaningless formula. Okay, next example type is related to these. We're told that A is a 4x4 matrix. We're told what the determinant of the adjoint is. And now we want to know what is the determinant of A. So we're going to use the same process, but we have to know what we're doing a little bit more. We'll be a little bit more careful. So A inverse equals 1 over the determinant of A times the adjoint of A. That means, by cross multiplication, it means that the adjoint of A is equal to the determinant of A times A inverse. So the determinant of the adjoint of A is equal to the determinant of, I'm copying the same thing that we've already done a few times. Determinant of A times A inverse. N is equal to 4. Since it's a 4x4 matrix, I'm going to take that scalar out. Determinant of A can come out front once for each row. So we have determinant of A coming out times determinant of A inverse. Okay, and it says that the determinant of the adjoint is equal to -2. That was given to us. All right. Next, I'm going to use that property that the determinant of A inverse is 1 over the determinant of A. So -2 is equal to the unknown determinant of A power 4 times 1 over the determinant of A. So -2 is equal to the determinant of A to the power of 3 using exponent laws. Now I'm going to take the cube root of both sides. So the cube root So the cube root of -2 is equal to the cube root of the determinant of A to the power of 3. The cube roots cancel. On the right hand side, the cube root cancels with power 3. So we have the cube root of -2 is equal to determinant of A. That's it, cube root of -2. Okay, next example. We have A is a 3 by 3 matrix, determinant of A is equal to -2, and we're asked to find the determinant of A times the adjoint of A. The key for a lot of these is to relate the adjoint to the inverse. I'm going to do that again. That A inverse is equal to 1 over the determinant of A times the adjoint of A. And then cross multiply. So adjoint of A is equal to determinant of A times A inverse. So we're going to use that up here. The determinant of A multiplied by adjoint of A is equal to the determinant of A multiplied by determinant of A times A inverse. Oh, yeah. Determinant of A times A inverse. I'm going to put that determinant of A out front because it's a scalar. It's still inside the big determinant. So determinant of A times A inverse. Oh. A times A inverse is the identity matrix. By definition, that's what you always get and multiply a matrix by its own inverse. And n is equal to 3. It's a 3 by 3 matrix. So we're going to factor this scalar out. So we have determinant of A to the power of 3 multiplied by the determinant of I. So we have determinant of A is equal to -2, so -2 to the power of 3. Determinant of I, determinant of the identity matrix, is just 1. It's a diagonal matrix. All the entries along that main diagonal are 1, and we get -8 as our answer. There you have it. So that's another type of weird example. We're not given the matrix, but we're given some information about the matrix, and then can you use some detective skills and some definitions, like what is the adjoint, what is A times A inverse, how do you factor a scalar out of a determinant, so knowing that it depends on the size, knowing that you have to factor that scalar out of every row. So using all that information to determine a value like this. And that is the end of the section, the end of the material for the course. As a summary of this section, 4.3, we saw that these determinants give us access to alternatives to row reduction for solving systems of linear equations. The first alternative is Cramer's rule, which is nice. It's a division of determinants. The second method is the method where we first construct the adjoint and then use the adjoint and the determinant to construct the inverse, and then use the method of inverses to find the solution to the system of linear equations. The downside, or the weak spot, or the deficiency of both of these approaches is that they don't work for non-square matrices, and that they don't work for any matrix that has a determinant of 0. For both of those situations, we have to go back to row reduction. And we would end up with either a family of solutions, if the determinant 0, family of solutions, or no solution. And then if the matrix is non-square, it can be anything. It could be a unique, family, or no solution, depending on the details. As a final summary of the course, Math 1229 is not a course in applications of matrix algebra. It is a course in the methods of matrix algebra. You are introduced to vectors, systems of equations, matrices, and then some aspects of matrix algebra, including determinants and applications of determinants. We did not dig into real applications of matrix algebra. We did not look at, for example, transition matrices, image and signal analysis, all the different methodologies and data analytics that require the use of matrix algebra and linear algebra. So we didn't delve into those. Those topics are usually reserved for courses that don't have algebra, matrix algebra, or linear algebra, or anything like that in the name. They might be courses that have this type of a name, business analytics, or courses that have this type of a name, management science. A lot of those types of courses assume that you have a background in matrix algebra like the one that we've covered inside this course. They may go a little bit further. They may talk about different types of decompositions. They may talk about something called diagonalization or matrix transformations. It just depends on the details. What you've seen will prepare you for what you would need for those types of courses. For other applications, for other uses of matrix algebra, this is not enough. If you're going to go on into honors economics and you're thinking about graduate school, or you're thinking about doing a minor in computer science, financial modeling, certain graduate programs in finance would also require more, I strongly advise you to at least take a look at Math 1600. It contains some material that overlaps with this course, maybe a fifth, maybe 1/6 or 1/7. Like, it's not a lot of overlap. You go through that overlap very quickly, and then you learn new stuff, and it's harder. It's proof-based, so sometimes in this course you've seen some proofs, but they're generally not like good proofs, and they're not hard proofs. So you don't know what a proof by contradiction is. All that we've done are direct proofs. So that's both an invitation and a warning. It's a much harder course than this. It is not the same course. It's 10 times harder. I'll just make up a number, but it is much more difficult. All right, and that's it.